Next we will see what is the equivalence between the asymptotic stability and exponential stability, particularly for the LTI systems. So when all the eigenvalues of the matrix A have strictly negative real parts, all entries of e to the power at would converge to 0 exponentially fast, and therefore the norm of that exponential matrix converges to 0 exponentially fast for every matrix norm. You can take any one norm, two norm, infinite norm, or the Frobenius norm, which also meaning to say that there exist two positive scalars such that the norm of this matrix is always less than equal to c into e to the power minus lambda t for all t belonging to the R. Okay. So in fact you can also see this equivalence from a logical proof also, since we know that the asymptotic stability, particularly for LTI system, because we know at the outset that for linear systems the response would be exponential in nature. So even if it is decaying or diminishing asymptotically towards 0, it will decay exponentially. So we have this uh, asymptotic and exponential stability equivalent, particularly for LTI system. So you can see a technical proof of also of this, that for a submultiplicative norm, if I compute the norm of the signal x, which is given by this e to the power at minus t naught for some initial condition x naught. So the norm of this quantity would always be less than equal to the multiplication of their individual norm. Right? And this one we can replace from here by replacing by the time t by t minus t naught. There exist two scalars c and lambda, and finally we obtain this, which is basically the definition of the exponential stability for LTI systems. So these two definitions are equivalent for LTI system. So the next question arises whether these two definitions are also equivalent for the time varying systems or linear time varying systems, which is not true. We will see a couple of examples later in the lecture that these conditions do not generalize to time varying systems, meaning to say that one can find matrix valued signals A of t that are stability matrices for every fixed t greater than equal to 0, but the system itself is not stable, meaning to say, let's say I have A of t. Consider one particular example, a11 of t, a12 of t, a21 of t, and a22 of t. Okay, now at a fixed time t, let's say at time t is equal to, let's consider three different time instants, t1, t2, and t3. So if I compute the matrices at these three different times, the matrix A might be a stable matrix, meaning to say all the eigenvalues of this matrices of this matrix computed at three different times are stable, but the system itself is not stable. Okay, so in that case we cannot say that these two definitions are equivalent for the LTV system, but we'll see more concretely when we will consider a couple of examples. So this is the key important theorem in the analysis of stability for linear system. The Lyapunov stability theorem provides an alternative condition to check whether or not the continuous time homogeneous linear time invariant system is asymptotically stable. So the first condition or the first test we saw that that given the system, you compute the solution. You compute the solution, basically you compute the state transition matrix, and then seeing the solution you could see whether the state or the output signal is bounded or not. Right? The second test is the eigenvalue test, where given the system, only for LTI system, this eigenvalue test is not valid for the LTV systems. So if you have an LTI system, you can do an eigenvalue test. But even if I do not want to compute the eigenvalues, this Lyapunov stability theorem provides a test whether you need to ensure the existence of some metrics which in fact give you the test for the stability. So here we don't need to compute the solution, we don't we don't need to compute the eigenvalues, but we will see some other different criteria, which is this one. So the following conditions are equivalent: the system homogeneous CLTI is asymptotically stable, which is equivalent to saying that the system is exponentially stable, which is again equivalent to saying that all the eigenvalues of A have strictly negative real parts. The fourth statement reads that for every symmetric positive definite matrix, so symmetric matrix, we know if we talk about the matrix Q, that the Q transpose should be equal to Q. Positive definite, that the quadratic form with the weight matrix Q is greater than 0. There exists a unique solution P to the following equation, which is also known as the Lyapunov equation, that is A transpose P plus P into A is equal to minus Q. Okay. Moreover, P is symmetric and positive definite, right? Which is equivalent to saying that there exists a symmetric positive definite matrix P for which the following Lyapunov matrix inequality holds, that A transpose P plus P into A is less than or 0. So here LMI is basically linear matrix inequality, not the Lyapunov matrix inequality. This LMI term is in general used for linear matrix inequality, right? So the next we would see the proof of this important theorem, because this, like we are seeing in the statement of this theorem, that here we, without even computing the solution or the eigenvalues, just by saying the existence of the symmetric positive definite matrix P, we can determine the stability, we can comment on the stability of the system, right? So since there are 5 statements, this is how we would going to proceed to prove all these 5 statements. So when we say that the statement 1 is equivalent to the statement 2, we mean to say that 1 implies 2, meaning to say if 1 is true, then 2 is true, right? Also the other way around, then if the statement true is true, then it implies that the statement 1 is also true. So when these two implications are satisfied, we say, which is equivalent to say that 1 is equivalent to 2. Okay, both ways implication is being satisfied. So 1 is equivalent to 2, that is exponentially stable and asymptotically stable. This equivalence we have already seen for the LTI system, that the exponential stable system and the asymptotic stable system is basically the same thing. Now, by the eigenvalue test, we can have the equivalence between the second statement and the third statement, that all the eigenvalues of A have strictly, do not forget this part, strictly, there should not be any eigenvalue with 0 real part. Okay, that's strictly negative real part, right? So this 3 equivalence we have already seen. Now the equivalence which we will prove in the next couple of minutes, that 2 implies 4 and 5 implies 2. Basically we want to close the loop, and the 4 implies 5 is quite trivial, meaning to say that if 4 is true, if the statement 4 is true, then the statement 5 is also true, and this it could be done by choosing Q as an identity matrix. Once you put Q as identity matrix of the same dimension in the Lyapunov equation, you would directly obtain this LMI. So 4 to 5 is pretty much straightforward. So the next we would see 2 implies 4 and 5 implies 2. Okay. So first we will see the 2 implies 4, meaning to say that if the system is exponentially stable, then given a symmetric positive definite matrix Q, this matrix Q is given, then the Lyapunov equation is satisfied for some p which is symmetric and positive definite. Okay. So in this implication, it is already assumed that the system is stable, is asymptotically stable. So to start with the proof, we claim that the unique solution to the Lyapunov equation is given by this. P is a definite integral from 0 to infinity given by this quadratic form, e to the power a transpose t into this matrix Q, which is given. The matrix A is also given. So basically you can compute the matrix P into e to the power at dt. So to verify this, so we are claiming that this is a solution. So to verify that this is actually a solution to the Lyapunov equation, being symmetric and positive definite, we need 4 steps to be proved. These 4 steps, that the integral defined in this equation 2 is well defined. That is, it can be computed. It has a finite value. The matrix P solves the equation Lyapunov equation. The matrix P is symmetric and positive definite. And finally, that there does not exist any other matrix than defined by this, which solves the Lyapunov equation. Okay, because this is a value. This is an improper integral from 0 to infinity. So let's see the well defined first. So this is a consequence of the fact that the system is exponentially stable. So it was already given that the system is stable. So now if you see that the system is stable, meaning to say all the eigenvalues are on the left hand side, strictly on the left hand side. So this exponential will decay. This exponential will decay. So finally this entire part would go towards to 0. So this integrand would, as t tends to infinity, would go towards to 0. So there exists a value. You can actually compute the value. If this integrand with t tending to infinity is approaching towards to infinity, then you could not compute any value. The value would be infinity. Basically, you are computing the area under this signal. Okay. So because of this, that these are exponential stable, or both these integral would die out as t tends to infinity. The integral is absolutely convergent. So we would have a certain value. Second, that this equation solves the Lyapunov equation. So this you can verify by putting this p into the Lyapunov equation itself, and then verifying whether the left hand side is equal to the right hand side. So in the left hand side, we put this p, which is given by a transpose p plus p into a. So I put this p integral from 0 to infinity here. So since this matrices A transpose and A are time invariant matrices, I could take inside the integral without affecting the value of the integral. Okay, so this finally I would obtain. But on the other hand, if I compute the derivative of this quadratic form, if I take the derivative of this quadratic form, this would come equal to this one, which is nothing but equal to this thing. Okay, so I can replace this whole term by the derivative of this quadratic form. Okay, so therefore this I can write the left hand side of the Lyapunov equation. I can write the integral 0 to infinity, this part, because this part has been replaced by this derivative of the quadratic form, and this you can compute by taking the value at 0 or by computing the value at infinity. So this I can write by limit t tends to infinity of this part minus at t is equal to 0. Okay, so see now that we already know that the system is asymptotically stable. So I know that these exponential as t tends to infinity would go towards to 0. So this part would entirely would become 0. Right? This part, since e to the power a transpose 0 is identity, so finally this one would become minus of q. So left hand, by putting this p onto the left hand side of the Lyapunov equation, I actually obtained the right hand side, meaning to say that this p satisfies the Lyapunov equation. Okay. The third point is about the symmetric and positive definite. So first we will see the symmetric. We know the definition of the the symmetric matrix, that the transpose of that matrix should be equal to the matrix itself. So first of all we take the transpose of that matrix, P transpose. Now carry forward it to the integral inside. We can compute the, we can simplify the transpose in this manner. So by using the transpose property, it would become e to the power at transpose. This term would become first q transpose, and the first term would go into the last with the transpose. Okay, so finally we would have e to the power a transpose t. Q is a given symmetric matrix, so we know that q transpose is equal to q. I can replace this q transpose by q, and the a transpose would nullify, right? So I can write this e to the power at. So if you notice that this in fact become equal to p. So we have verified that P is a symmetric matrix. Now for the positive definiteness, we define an arbitrary vector Z of the same dimension n, which is given by Z transpose PZ. Again, by putting the P matrix, the P integral defined earlier, into this part, we obtain this. And finally I replace this part Z transpose e to the power a transpose t, or to be precisely e to the power at into Z, by another signal wt. So see, if you take the transpose, if you take the w transpose, you would obtain Z transpose e to the power a transpose t, which is this part. So I can write this as w transpose q into w. Okay, so we know that q is already a positive definite matrix. If q is a positive definite matrix, then I know that this part would be greater than or equal to 0. We will come on to this part, equal to 0. We know for positive definiteness, the equal to part should not be 0. Since Z could be any arbitrary vector, so we are not sure whether it would be greater than, only greater than equal to, greater than 0 or greater than equal to 0. So let's see. So we know that it would be 0, that Z transpose PZ would be equal to 0 if this part is equal to 0. Okay? Now notice here that this part, this is a quadratic form, that this part would go to 0 only if this Wt signal is 0, because Q is a positive definite matrix which can never become equal to 0. W2 equal to 0, meaning to say e to the power atz is equal to 0, and e to the power at is a non-singular matrix already. So this will become 0 if and only if z is equal to 0, right? From which one conclude that z is equal to 0 because e to the power at is singular. Therefore P would always be a positive definite matrix. Okay. Now the fourth one is the uniqueness property, which is meaning to say that there exists only that P and does not exist any other P. So let's assume that there exists another solution given by P bar which also satisfies the Lyapunov equation, and this P bar is different than the P defined in the equation 2. So here we write the P in the Lyapunov equation and P bar which also satisfy the Lyapunov equation for the same Q. So if we subtract these two equations, we obtain this equation A transpose P minus P bar plus P minus P bar into A is equal to 0 because the Q matrix remains the same. Now if I multiply this equation, pre-multiplying and post-multiplying by e to the power A transpose T and e to the power AT, I can do this because both these matrices are non-singular matrices. Okay, so I can pre-multiply by this e to the power N transpose T and post-multiply by e to the power AT. The right hand side would remain as it is, equal to 0. Okay, now if you pay a close attention to this one, it is actually the derivative of this part, of this quadratic form, e to the power A transpose T P minus P bar into e to the power AT, which becomes equal to this. So what it says, that the derivative of this one is equal to 0. So meaning to say that this term would either be equal to 0 or would be equal to some constant value. and this is what it's that must remain constant for all time. But because of stability, this quantity must converge to 0, because A is having all the eigenvalues on the left hand side. So this part or these two parts would go towards to 0 as t tends to infinity. Meaning to say that this form would become equal to 0 only if this weight matrix become equal to 0, right? So meaning to say that P minus P bar equal to 0, meaning to say P would always be equal to P bar. So there does not exist any other matrix than P. Certainly for different Q there would be different P, but for the same Q there could not be two different P. This is how we define the uniqueness. Okay.